Okay, so you would, if we look again at it, so if you go from, this one stays the same and it's first order, so we just ignore this column, all right? And m is second order, so if I triple m, I times that by 3, this must go up by 3 squared. So it'll go from 0.05 to 0.45, okay? L is still staying the same, so if I go from 0.45 down to 0.15, this is going to divide by 3. Okay. Now remember, this must be the square of this because this is a second order reactant. So if I change the total rate of reaction by 3, then this must have been changed by the square root of 3 because whatever change I make to this, I must make the square of that change here. Okay. Now, so up until this point, I've wanted you to do it this way. Okay. Now, at this point, yes, there is another way of doing it, okay? The reason I didn't tell you, some of you have obviously worked it out, but the reason I didn't tell you about it before is because you will need to be able to analyze data like this from reactions, okay? So I wanted you to be able to think about how changing these quantities would change the rate, okay? And it's really important that you are able to look at these numbers and sort of make sense of the numbers themselves. So when you see a 0.1 here and a 0.3 here, you can see a 0.05 and a 0.45 here, all right? And they're not just random numbers in a table. You can see the relationships between the numbers. And the other way of doing it sort of bypasses that, that way of doing it, that way of understanding the numbers. So what you could do, equally, is you could rearrange the rate equation, okay, to find K. So K equals rate divided by Lm squared, okay? And then you've got a complete set of data here. So you can put these numbers into this equation here. All right, so let's do that. So I know that if I have K equals rate divided by Lm squared, I know that the rate here is 0.05 divided by L, 0.1 times 0.1 squared, which will give me 0.5 divided by 0.1 cubed, will be 500. So that's my rate constant. All right. So now I know that if I do the next one here, I know that rate will be 500 times my concentration of L, 0.1, times my concentration of M squared, 0.3 squared. So if I do that, I do 500 times 0.1 times 0.3 squared, and I get 4.5, which is not right. Or if I made a mistake. Oh, sorry, I've made a mistake here. So that should be 0.05. 0.05 divided by 0.1 cubed is 50. So that's 50. Okay, so that's 50. So if I do 50 times 0.1 times 0.3 squared, gives me 0.45. 0.45. All right, so that's one of the reasons I don't like this method so much, because it depends on your calculator work. So you need to be really good with the calculator, you need to be really good with rearranging equations, because now if you look at the next one, I want to know what m is. Okay, well, m, you have to rearrange this equation to get m. So if I rearrange it, I'm going to get rate divided by L times K, all square rooted. Oops. All right, so that's my, remember my initial rate equation is rate equals K L M squared. If I rearrange it for M, this is what I get. So now I put the numbers in. So the numbers for this one are, the rate is 0.15, so it's 0.15 divided by L, 0.1 times my rate constant, which is 50, all square rooted. Oh, you can't see that either. Okay, there you go. All right, so it's 0.15 divided by 0.1 times 50, all square rooted, gives you 0.173, 0.173. Okay, so you can do it that way as well, all right, but it's really important that you realize that these aren't just random changes in numbers, that any change here is related to the change here, and you need to understand what that relationship is, because there will be questions where you have to do the reverse. So you will be given these numbers, and then you have to work out the order with respect to each one. And if you can't work the relationship between the numbers, you won't be able to do that. All right, but yeah, obviously you can do that as well. If we look at C and D, okay, so this is what I'm talking about. So now we need to work out the rate equation. So what we do is we look at here, Q stays the same. So any change between these two is not because of Q, because Q hasn't changed. So what we can do is we ignore Q for the moment, all right? Because Q isn't changing. I should put that there. All right, so any change in the rate is due to a change in P, okay? What's the change in P? The change in P is times by 2. What's the change in the rate? Change in the rate is times by 2. So I double P, the rate doubles. So P must be first order. All right. So now I can look at what the order is with respect to Q. So I can't use any of these because these are all the same. So I need to use these two here where Q changes. Okay, so Q changes by 2. All right. And what change do I do to P? Well, I do P is going up by times by 4 divided by 3. All right. And what is the change here? Well, if I do 0.1598 divided by 0.00603, oh, no, that's not right. 0.01598 divided by 0.00603, it's a change of 2.65. So, times by 2.65. Okay, and 2.65 is if I divide that by 4 divided by 3, it's twice that. Okay, so this change here, 2.65, is twice this change. All right, which means that this must be first order as well. Okay, now that's not always very obvious. So if we look at it like this, okay, let's suppose that I have P is 0.3 to 0.4, and my rate is 0.00603. Okay, now if P is first order, what change would I expect there to see? So if I times this by 4 over 3, this is first order, so I'm going to times it by 4 over 3 as well. Okay, so I get 0.00603 times by 4 divided by 3. Okay, I get 0.00804. Okay, so if I was only changing P, that's what I'd expect to see. Okay, but actually I don't have 0.00804. I have, it's actually 0.01598, okay, which is times by 2. Okay, so this times by 4 over 3, this is due to P. And this times by 2 here, this is due to Q. All right, and you can see that this combined with this, so if I take this number here, I times it by 4 over 3, and I times it by 2, I get the rate that I've got. This part is because of P, this part is because of Q. So Q has gone from 0.1 to 0.2, so I've times it by 2. Okay, so a change of times 2 in Q has given me a change of times 2 in the rate that I can attribute to Q only, which means that Q is also first order. Okay, so down here I can do the same thing. All right, so what I want is so I've got 3 reactants. I want 2 experiments where 2 of them stay the same and 1 changes. Okay, so here these are the same, these are the same, this one changes. Okay, what does it change by? It changes by 4 divided by 3. Yeah, because if you do 8 divided by 6, that's 4 divided by 3. And what is the change here? Well, if I do 2.4 divided by 1.8, I get times by 4 divided by 3. Okay, so I've changed this by 4 over 3, I've changed this by 4 over 3, which means that this must be first order. Okay, so what I could do is down here I could write rate, I could write out my rate equation, K, H plus, with a gap here, CH3, CO, CH3, with a gap here, and I2 with a gap here. Now I know that this number here is going to be 1. All right. So now I can look at, because now I can use a number where this one changes because I know what the order is. So let's look at these ones. Okay, so H plus stays the same. This goes up by 4 over 3 times by 4 over 3, which means that here I'm going to get times by 4 over 3, and then any additional change will be due to I2. All right, so if I take 9 times 10 to the minus 5, oh no, let's do it the other way, let's do this one divided by this one, 1.2 times 10 to the minus 4 divided by 9 times 10 to the minus 5, that's a 4 divided by 3 change. Okay, so I've changed this by 4 over 3 and it's first order, and I've changed this by 4 over 3, which means that all of the change in this is because of the change in this, which means that this change here has no effect. So I2 is 0 order. All right, and you should therefore be able to work out H plus. All right, I suggest you use this experiment and this experiment because this doesn't change and this doesn't change. All right.